So I was pretty happy with this. If you are not happy with the grade you have sitting in front of you, you should come talk to me. You should review the key that was posted to our Canvas page yesterday. So you have the answers I was looking for, as well as what you provided me, and we can talk about the differences in what happened and where to go from here. I was pretty happy to see an average as high as 77. That's really quite nice. Those of you with any statistics, that's a standard deviation and a high and a frequency distribution. So we're going to have those sorts of statistics available to us on a regular basis. If you have specific questions about what you were looking for, what you think I was looking for, what you thought you said versus what I read, come talk to me. Be glad to discuss the exam with you at your leisure. Meanwhile, we're going to move on. I have question. Oh, there are two scores in that range. Two scores between 90 and 100, two scores between 80 and 89, four here, and none there. That's a distribution of the scores across the ranges. There are lots of different ways to describe the statistical breakdown, a dozen people. Kind of hard to get a good large picture, so I just do. Thank you. You're welcome. Okay. Again, my goal is to expand the types of functions we can do derivatives on. With that in mind, let's add trig functions to our pile. Let's start with something easy. Right now, I have no shortcut formula that I know for how to take the derivative of sine of x. If I don't have a shortcut, I need to do it the long way. And that means I got to go back to my limit definition. So let's do that. If I want f prime of x, that is the limit as h approaches 0, f of x plus h minus f of x over h. So I'm going to plug sine of x into that. And here is my first non-trivial problem. What am I supposed to do with that? Dean? Unfortunately, that would be really nice, but that isn't what happens. But I would like to be able to break it up to do the sine of x and then other stuff. Somewhere in the appendix of all of the trig stuff that we did. So that's what, appendix D in the back of the textbook. There should be a bunch of trig identities, which I'm sure you all remember perfectly well. Me neither. On our Canvas page, on the other hand, way down here, under all of my reference sheets, reference files, I see one labeled trig, long trig formulas. Let's go there. So I don't expect you to have this memorized, but we can at least look it up. If I go to that long trig formulas folder, file, Here's a PDF of all of the trig formulas that I did in the trig class that I, of course, have memorized. No, hell no. So let's take a look right here at the top. It says sum and difference formulas. Well, that's what I'm trying to take. I'm trying to take sine of a sum. And there's a formula for the sine of a sum. Third one down. So this is the problem, Dean. When I do the sine of a sum, it's a lot more complicated than that. I used alpha and beta instead of x and h, so it'll be sine of x plus h gives me sine of x cosine of h plus cosine of x sine of h. So I'm going to use this where I see the sine of x plus h. So with the formula in front of me, limit h goes to 0, sine of the first thing, cosine of the second thing, plus cosine of the first thing, sine of the second thing. And that only replaces sine of x plus h. Like that. These pieces replace this. Bleh. That's disgusting. But it's not as bad as it could be. Because what I see is this is a sine of x piece. This is a sine of x piece. This doesn't have any sines of x's in it. So let's move this to the end, switch these two together. So I'm just rearranging. Phew. Now, excuse me. The rest of my work from here on out is going to deal with trying to rearrange and figure out what this limit works out to. I'm adding. I've got pieces that have sine plus piece that doesn't have a sine of x, it only has a cosine of x. Let's split this, since I'm adding, into two separate pieces. I'm going to break it like that. You with me so far? Most of this at the moment is kind of just algebra mess. But I look at that far right term and I say to myself, this is a limit in terms of the letter h. It doesn't care what x is doing at all, right? As I take the limit as h goes to 0, cosine of x doesn't change, which makes it, in terms of h, a constant. What can I do with constants with limits? Take them out front, right? So I can rewrite this piece as cosine of x, and then limit as h goes to 0, sine of h over h. I can also do something similar with the piece on the left. What can I do there? Exactly. There's a sine of x in both of those pieces. So if I factor out the sine x, I pull it out front, I get sine x times some other limits. Now I just need to know what happens with those. If I pull out the sine of x, what's left on top? Cosine of h minus 1. Great. So now I need to answer the question, what's in the box? But wait, I've seen this before. This one right here was one of the very first limits we did. Back in chapter 2. We did it with a graph. Then we kind of proved it. We showed why we think it's true with that little picture of a triangle inside a circle. But that was like 2.5 weeks ago, maybe longer. What's the limit in this box? Sine of h over h. Yes, teacher. One. Exactly. Page 85, bottom of the page. That was the graph we did. There's a hole in the graph, but the limit works perfectly fine. I'm going to take that and run with it. This box has a value of 1. Uh, what about this? I don't know that one yet. I don't have a nice, because if I plug in 0, I get cosine of 0. What's cosine of 0? So the top is 1 minus 1, that's 0, but the bottom is also 0. So that's an indeterminate form. And that means I have to fix it. I have to determine it somehow. So I'm going to step off for a moment, grab another sheet of paper, and I'm going to do just that part. Now, when I was doing indeterminates, I tried to factor, but I don't have any powers to try and factor out here. There were a couple of ones where I tried, instead of to factor something out, I multiplied something in. And I would multiply by 1, because that's the only thing I know how to multiply by that doesn't change stuff up, is 1. But I can make that 1 look however I want. So I'm going to multiply by 1. But the one I'm going to pick is going to be the opposite expression here. The conjugate, cosine of h plus 1 over cosine of h plus 1. Now, I'm pretty sure you're all looking at me going, what the f? I promise this gets better. I'm not going to touch the bottom for the moment. I'm just going to leave the bottom as h times cosine h plus 1. But what happens when I multiply out the top? Great. Cosine of h squared minus 1. Hey, wait a minute. It's not multiplied. That's subtracted, right? Squared, outer, inner, last. The outer and the inner cancel out. So it's minus. It's actually subtracted. It doesn't multiply at this point. But I can pull another identity out of my pocket. Fiona? Almost. What's the relationship you're using? They add up to 1. So I say to myself, wait, sine squared h plus cosine squared h is equal to 1, right? So let's rearrange this. I'll move the 1 from that side to that side, and I'll move the sine to that side. So I get cosine squared h minus 1. When I move that over, it becomes negative sine squared h. So yes, I do get a sine squared, but it's a minus sine squared. So equals limit h goes to 0 minus sine squared h over h times cosine h plus 1. In the back of your mind, I am sure what you are saying is, Dr. Sassmore, this isn't getting any effing nicer. It still sucks. Yes, it does. So I'm going to fix that right here. Sine squared means sine times sine, right? So let's break those into 2 separate signs. The minus sign goes out. Limit h goes to 0. I have 1 sine of h. I'll put that over the h. I have another sine of h. I'll put that over the cosine h plus 1. Because they're multiplied together. That means you multiply the tops and you multiply the bottoms. With me so far? The reason I'm really happy to see this is there's that same limit again, isn't it? And when I'm taking the limit of things that are multiplied, I can take the limit of each one. So I get the limit as h goes to 0 of sine of h over h times the limit as h goes to 0 sine of h over cosine h plus 1. What's this? 1. What's this? Let's just try to plug in. If it works, it works. If it doesn't, I'll have to do something else. But if it works, it works. What do I get? I get 0 over 2, which is 0. Wait a minute. Minus 1 times 0 is 0. This whole limit worked out to be 0, right? Where were we using this? I go all the way back to this box. This box is what we just computed. We've resolved our indeterminate. That's now 0. So I have sine of x times 0 and cosine of x times 1. And those are added together. Wait a second here. You just showed that the derivative of sine of x is cosine of x. Period. End of story. And now I have a shortcut. Whenever I see a sine of x, I know what to do. It wasn't a very short to get there shortcut. It took us about 15 minutes, but we figured it out. And now I can just keep that in my toolbox and use it whenever I want. Hot damn. If I want to, I can go through this exact same process again, because you'll notice in this file that we were just looking at, the one we were looking at was sine of a sum, right? But the top line there is cosine of a sum. So if I were going to do cosine of x plus h, I'd use this formula instead, right? I'd do the same damn thing over again. But please notice what's different between that top formula and the third formula. There are a number of things that are different. See?
First one's cosine, sine.
So it's cosine and cosine, it's sine and sine, and there's a minus in between, not a plus. The cosine h part was the part that gave me the 0, right? So it'd be cosine of x and cosine of h. That's the first part. The sine of h is the part that gave me the 1. The cosine of h part's the part that gave me a 0. If I go to do this again, and I go to work on the derivative of cosine of x, I'm not going to get cosine. I'm going to get sine. But I'm going to get it with a minus on it. Well, this makes me really, really happy. Because now I have sine, I have cosine. There are other trig functions, right? How many more? Tangent, secant, cosecant, and cotangent. But all 4 of those can be built from sine and cosine, right? How do I write tangents in sine and cosine? All right. Commit, people. Tangent is the other way around. Sine over cosine. Because if it's cotangent, the co goes on top. It's the only way I can remember it. Sine of x over cosine of x, that's our tangent of x. So if I want the derivative of tangent of x, I can use sine and cosine and do the quotient rule. Quotient rule to the rescue. We did the quotient rule on Monday. I have a top and a bottom. Let's walk through the formula. Derivative of a quotient. What do I do?
Times the bottom derivative, the bottom half the top derivative.
I got to be careful about the order in which I do those. So which one goes first?
The bottom, the top.
Which one gets a prime? The top prime or the bottom prime in the first one? It's the derivative of the top times the bottom, then the derivative of the bottom times the top, and I'm subtracting. So I start with the derivative of sine. What's the derivative of sine? We just did that. Cosine. Derivative of the top times the bottom minus derivative of the bottom. What's the derivative of the cosine? Perfect. Derivative of the bottom times the top over the bottom squared. Marvelous, wonderful, wonderful, beautiful. What happens on the top there? Elena? That's 1. Because that's cosine squared plus sine squared. And we just remembered that was equal to 1. I cannot cancel the cosine on top with the cosine on bottom because there's the addition. But since it adds up to being 1, I can replace it. Wait a minute. 1 over cosine squared is the same as 1 over cosine all squared. Because 1 squared is 1. So the top is a square, the bottom is a square. I can think of the whole thing as a square. Say it again. Secant. 1 over cosine is the secant function. The derivative of a tangent is secant squared. I would like you to do cotangent for me. Cotangent is cosine over sine. I apologize to you all. The link I showed you for Calculus the Musical has a bunch of songs that have these rules in them. The quotient rule is low de high, high de low, over low, low, and they do it to Cab Calloway, doing Minnie the Moocher at one point. They do it to a bunch of different tunes. All of the trig derivatives are done to Adam Ant's Goody Two Shoes. That song is older than all of you. It was a popular song when I was a very young child. So the problem is it's stuck in my head now. So I'm sitting here whistling Adam Ant, who's not been on the charts since well before the 90s. But the tunes stick. With, again, a similar amount of work, where do I finish? Because I end up with -1 over sine squared. secant is 1 over cosine. I can do the quotient rule. Cosecant is 1 over sine. I can do the quotient rule. The derivative of secant of x is secant x tangent x. The derivative of cosecant of x is minus cosecant x cotangent x. Nope, doesn't help if I wrote them where you can't see them. But something interesting has just happened here. Derivative of sine is cosine. Derivative of cosine is minus sine. The derivative of tangent is secant squared. The derivative of cotangent isn't cosecant squared, it's minus cosecant squared. The derivative of secant is secant tangent. The derivative of cosecant, cosecant, cotangent with a minus sign. Every time I swap a function for the cofunction, I get an extra minus sign. I do not want you memorizing these. This is a pain in the ass to memorize. The following will be attached to your next exam. You get those for free. And there's all 6 of them. Derivative sine is cosine, derivative cosine is minus sine. Tangent is secant squared, cotangent is cosecant squared, secant and cosecant. I absolutely love the fact that as soon as I figured out 2 of these, I got the rest of them by using rules we already have. I am a lazy human being by definition. I want to do as little work as I can get away with. And that means building on all the stuff I've done before. So using my limit definition once, well, in this case, twice, I really didn't go through doing cosine, but I waved at it. I did sine and cosine, and then did have to do another limit definition after. This table is also in the text on page 194. So grab a Post-it note, stick it in the textbook, put a flag or a star on the PDF page in your electronic version if you have that. Questions? I did actually have in the book the proof of this limit with the angle and the picture, so we could actually go through the. I didn't think you wanted to see this. So we drew this picture a couple of weeks ago, and that's really enough. If you really want to walk through the geometry of it, we can do that, but I think that's beyond where we want to be. But now I put all of these ideas together. My trig functions are used as position functions. I'm going to take a pendulum, pull it off to one side, I don't know, 2 feet, and let it go. If this is 2, I'll call this side -2, and I'll call 0 right in the middle. Well, from your perspective, 2 minus 2, 0, right? If I start over here and I let it go, it's going to go back and forth and back and forth. That's a trig function. If my position at time t is given by 2 cosine of t, well, now you can tell me how fast it's going at different times, right? What's the velocity at any given time? How do I get from position to velocity?
Mhm.
I take a derivative. Because if meters to meters per second, that's change in, that's exactly what a derivative is. Derivative of cosine is, and what do I do with the two? It's being multiplied, so I just keep it. At a given time, say at time 0, time 0, we're all the way to the right, because S of t will be 2. A cosine of 0 is 1, so S of 0 is 2. But we're moving that way, because our velocity is negative. After (1.57 seconds), time is pi over 2 now. Where are we? I pull the thing over to the right and I let it go. At time 0, it starts to fall back towards the middle. Where are we at pi over 2? We're at 0. So we're here. And which direction are we moving? We're still going. Oh, wait a second. That's not right. We're still going this way, aren't we? I didn't do it right. What is my velocity at time 0? My velocity is 0. Why? Because I was holding it. I hadn't let it go yet. It wasn't moving. Gotta remember that part. When I get to time pi, 3.14 seconds. Where am I? S of pi, 2 cosine of pi. Cosine of pi is -1. We're at -2. We've made it over here. And our velocity is, again. So what happened? Tick. And then as I let it go, it's going to go back the other way, and it's just going to keep going. Simple harmonic motion. I can go a step further. I didn't do anything about acceleration. How do I know the acceleration at any point in time? I take the derivative again. Because acceleration is change in velocity. That's meters per second, meters per second squared. So V is S prime of t. A is S double prime of t, or V prime of t. But wait a minute, the velocity was -2 sine of t. What is the acceleration function? A of t.
-2%.
Now that actually to me is really very interesting. My position is 2 cosine t. My acceleration is -2 cosine t. So if I'm all the way over here at t equals 0 at a position of 2, my acceleration is -2. Which makes sense because I'm going to start moving this way. Right? So I'm going to go from being stopped to moving this direction. A change in velocity is accelerating. When I get over to this side, I come to a stop again, but I want to start moving this way. So my acceleration is changed. My velocity changes direction. I went from moving to the left to moving to the right. And that's 55. I started all the way over here on the right. My velocity is positive, my acceleration is 0. So I start moving. At time pi over 2. My position is 0. What's my acceleration? We didn't do it up here, but we could. Right now that we have the acceleration formula, I can ask what is the acceleration at pi over 2? It's 0, which means I stop speeding up. Think about your object moving. As it falls, it gets faster and faster and faster, right? Then it hits the bottom and it starts to go up. What's it start doing in terms of its acceleration? It starts to slow down because gravity's pulling the other way. And it comes to a stop at this side. And then it goes back the other way. My acceleration is in exactly the opposite direction of where I am. Suppose, let's make this a little easier. Suppose you are in a car. And I tell you that this car, crappy drawing or not, is going this way with some velocity. If I accelerate that way, what will happen to my speed? If I accelerate to the right, my speed goes up. What if I accelerate to the left? How would you accelerate to the left when you're moving to the right? I have brakes, right? That's what a brake does. It accelerates you in the opposite direction. What happens to my speed? It decreases. By the way, there are other ways other than brakes, but not for cars. If I am in a plane, as opposed to a car, I have an engine, right? The engines point that way. The sides of my wings, the engine point behind me. The next time you get on a plane and you watch the plane land, watch what happens to the engines. As you land, the engines open in the front. And instead of pushing air out the back, they push air out the front. It's called a thrust reverser. It's an acceleration in the other direction. It's the opposite of an afterburner. It's a forward burner. It causes the plane to accelerate in the other direction. If your speed and your acceleration point the same way, you're going to get faster. If they point in opposition to each other, you're going to slow down. Regardless of whether you're going left or going right, you're going to slow down. 90% of the reasons calculus was developed outside of geometry were to solve problems in physics. And I'm going to sound like the most sanctimonious SOB on the planet. The language the universe speaks is math. I didn't make that quote up. That's Galileo. If I want to be able to know why things do what they do in front of my face, I need to speak this language. Questions? Talk to me. If I let that pendulum go and it starts swinging back and forth, it's not really going to swing forever, is it? It's going to run into air resistance, right? And that would make it slow down over time. But there's another thing that can happen. If I happen to take the pivot, that my pendulum is hanging from, and move it ever so slightly, pushing it in sync with the pendulum, I'll add energy into the system and I'll keep it from slowing down, right? I can overcome air resistance. This can happen naturally from the wind. If I have an object vibrating with this simple harmonic motion, and the wind comes along and blows at just the right speed, it will cause another vibration. And that vibration can push my pendulum faster and faster. It turns out this is the idea of resonant frequencies. And you've all seen this if you watched any of the Harry Potter films. Yeah, I know, I'm pulling up real, where the hell did you see this in Harry Potter? Do you remember? I think it's in the second movie or the third movie. They walk up to the portrait. They never give her a name in the movie. It's just called the Fat Lady. The Fat Lady who's the guardian to the entrance to Gryffindor. And she's trying to break a glass with her voice. You ever seen somebody actually break a glass with their voice? It's bizarre. They have to sing the exact right note to make the glass vibrate. So they ping the glass and they start it vibrating. They listen to that note, and then they start to sing exactly that note. And it makes the vibrations faster because it resonates. And what happens is the vibrations get bigger. Instead of getting smaller, like our air resistance is doing, the vibrations get bigger. Well, if I've got a vibrating item, it's like a cosine, right? We had 2 cosine of t. If I start adding more stuff in, it starts to get bigger. And the easiest thing for me to think about is a graph that gets bigger and bigger and bigger as I go off in this direction. What's a graph that looks like this? Getting bigger and bigger and bigger in this direction. Say again? An exponential. An e to the x. So what if I change this and it becomes e to the t times 2 cosine t? Well, now if I want the derivative, actually, what I really want is the second derivative, because I want to look at the acceleration. So let's do the first 2 derivatives of this. We'll start with just the first derivative. What do I have to do to the first derivative? To do the first derivative, what do I need? What rule do I need? Power rule. Unfortunately, no, because power rule only works for x to a power, in this case, t to a power. I need the exponential, but I need It's E times cosine. I need the product rule. I really want to think of this like this as a product. So when I do the derivative, S prime of t, that's the velocity. What's the derivative of e to the t? Because it's e to the x. If it's e to the x, that's great. So derivative of the first times the second plus leave the first alone and do the derivative of the second. What's the derivative of cosine of t? Great. But also, oh crap, because I really want the acceleration. I want the second derivative, which means I have to do the product rule again twice because I'm going to have to do it. Oh, wait a minute. No, I can make this a little easier. I can do some algebra. Dean, what can I do? Right. All right. It is 2e to the t times cosine of t minus sine of t. Then I only have to do the product rule once. So sometimes the algebra helps us and sometimes it's not worth it. This time it was worth it. So I go to do the second derivative. S double prime of t, that's v prime of t, that's the acceleration. Derivative of the first, leave the second alone. Then leave the first alone. Do the derivative of the second. What's the derivative of cosine? What's the derivative of sine? But they're subtracted. What happens? Something really nice happens. Okay. This cosine is positive. This cosine is being subtracted, right? So what happens to those cosines? Because they both have a 2e to the t in front of them. They're perfectly balanced. They cancel each other out. But what am I left with? I'm left with a negative sine t times 2e to the t and another negative sine t. So I get two of them. That means instead of having 2e to the t, I have 4e to the t. Minus 4e to the t sine t. My acceleration got bigger, right? It's still pointed in the other direction, but it's bigger. Do me a favor. Let's graph this. 2e to the x cosine of x. Grab your calculator. Let's graph that stuff. I'm going to graph this on the standard window, minus 10 to 10, minus 10 to 10. I can barely see it. I can barely see it. But here we go. We start at time 0. Holy moly, look. Boom, boom, boom. That's going to go back and forth, but it's going to get mind-blowingly huge, right? So I'm trying to think this little bitty glass wants to move back and forth a huge amount. What happens to the glass? It shakes itself apart. Because I was able to put energy in and make those motions bigger. This is not unique to glass. I would like to introduce you to a bridge. The Tacoma Narrows Bridge in Tacoma, Washington, known as Galloping Gertie. Why would you call a bridge galloping? The first bridge that they built, 1940. There's the picture right there. They built it over the Tacoma Narrows. The Narrows is a gorge where the river runs, the Tacoma River. And then they started building it. They finished. It's a suspension bridge. You see the cables? And then it started to move in the wind. It started to vibrate up and down as the breeze pushed the vibration that everybody walking was making the bridge vibrate at. That's the same bridge in that picture, buckling in the wind. It tore itself apart. There's an absolutely mind-blowing film of this. All I did was go. The Tacoma Narrows Bridge shook itself apart due to exactly this resonance idea. If you go out on Route 30 and you drive into Pittsburgh, you will cross the George Westinghouse Bridge. It's on the other side of North Versailles from here. There is a sign on the side of the North Versailles Bridge, of the Westinghouse Bridge, that says break cadence. What's a cadence? It's a rhythm. You are not allowed to march across the bridge in rhythm, just in case the rhythm you set up is the right one. Useless crap. I'm never going to use this. It tore down a bridge. Now, the bigger problem is that I was talking about the pendulum just on its own slowing down. If I want a function that slows down, I shouldn't be using e to the x. I should be using this one. What graph slows down like that? Instead of the e to the x like this, I want it to do this and slow down. Yes. Which is the same as e to the negative x. I can do the quotient rule, right? How do I deal with it when it looks like this? That, hold that thought, promise, I'll address that. That's actually a really important idea. But before I get to that, I'm reminded that we just did a limit. We did the limit as h went to 0 of sine of h over h, right? Well, this actually allows me to do some other indeterminate forms that we couldn't do before. What if I had the limit as x goes to 0 of sine of 6x over 5? I'm sorry, 5x. That's not the same thing on top and bottom, right? I can't do that. It's still going to give me 0 over 0, but they don't match like this one does. If they matched, I know this limit is 1. So this should somehow be related to that. Well, it turns out that I can play with my limit laws here. The 5 on bottom is a constant, yes? So let's pull it out front. Unfortunately, Dean, as we saw earlier, I can't take the 6 out of the top, because then I would have just had a whole lot easier of a time doing the first part of the day. So what if I don't take it out, but I put it in? Let's multiply by 1 again. But the 1 I'm going to multiply by is 6 over 6. 6 is a constant, yes? On the top, take that constant out front. But now what do I have on the bottom? I left the 6 on the bottom, didn't I? So the 6 on the bottom will stay with the x. What's this limit? Because that's this. If I have limits that are almost the one I want, I can adjust and end up with the one I do want. Questions? The limit of the cosine part gets used far less frequently, and we'll develop other techniques for doing indeterminate forms as we go on. It's this thing. Because that's really the important piece about this idea. I want to deal with air resistance. I want to deal with friction. I want to deal with the oscillations that slow down over time. If I had a bump in my car, I don't want my shock absorbers to make me look like I'm in a lowrider. No, it's not going to work for me. I'm not going to make it here in one piece if I keep bouncing my head off the roof of my car. So I need those vibrations to slow down over time. That's that e to the minus x. That is tomorrow. But how are we doing tomorrow? What's the schedule say? The video will be posted just like it was for the snow day. The notes will be posted just like they were. They will be available to you online. Monday is question and answer. If you are available during our class time and or the class period before, I can use some help with the middle school math competition. Please come by. We'll be in Sicilian Hall starting around 8. Thank you. Have a wonderful day.